Hello, welcome to option B, of project 6. So we're going to look at a new application of GANs. It's relatively recent and it's a little more complicated than some of this stuff, but I think it has some really cool applications. So I wanted to go over the code and give you the option to look at this for this. So again, we start up as normal. We we'll input our libraries in just a sec. Let's just talk a little bit about what CycleGAN is. So if you've done the learning practice exercise before this, you've learned what basic GANs is, generative adversarial networks. They have a two-part network, one that generates like an image, and then a discriminator that looks at the image at the generated image and a real image and tries to figure out which one's real and which one's fake here. And so that's what the adversarial part of this is related to. CycleGANs work on something slightly different in that in a normal GAN you need paired images. You need one image of like a picture of a person with glasses and then the same person without glasses, or a black and white image and a color image of the exact same thing. CycleGANs don't work the same way. They're similar, but we don't need these what are called paired training data. But we'll try to copy the style of different things. So they're used to do things like convert from a summer picture to a winter picture, a picture that's like a photo and a Monet style image for this. They also can be used to convert like pictures of horses into zebras and back and forth for this. We'll be looking at this, taking a photo and make it look like Monet painted it aspect. So the structure's not that different, but we do have a kind of duplicate structure. So it's kind of like two GANs working together. So the first one will take an input image and use a generator, an encoder and a generator to generate some stylized version of this input. And then we'll compare that to an actual stylized or version of this. And the discriminator will try to say that this is real or fake. So this is kind of like a traditional GAN. But also we take the same thing, feed that into a coder and encode it back to the original way. So basically we're like translating it into one format and then translating back to the original format. And then we're having this discriminator look at this final version and the original version that has been translated and translated back. And this is why we don't need necessarily paired outputs, because we're looking at the same image that's been translated and translated back here. Now these structures here where we have an encoder, we create some internal representation and we have a generator. This is kind of how they look. They get a little more complicated here. Where we have a number of convolutional filters. We have things that are similar to convolutional filters, but they're called residue filters because they also include some links around the convolutions here, and then some kind of inverse convolutional filters that rebuild the image here. So if you want to learn more, there's a paper here about CycleGANs. So here's where we're going to load in some data here and bring in our libraries for us. We're also going to declare some stuff. Now, you might want to switch this. Some of this training takes a while, so you might want to switch the runtime to use a CPU or a TPU tensor processing unit that speeds up a lot. And this is some code set up to make use of TPUs if you're going to do that. So you don't need to use a CPU or a TPU, but it does increase. Some of this training time takes quite a while, so you might want to switch it up to a TPU or a CPU here for this. Okay, so we're going to look at a Kegel challenge here. This is kind of a learning challenge. It's in Kegel. I'm something of a painter myself is the name of the challenge. And it uses GANs to create art in a Monet-like image for this. So brief description here that we're going to try to create GAN to generate images. We have a bunch of images in Monet style, and then some just normal photos that you'll work to generate things with. So that's the general idea. You can look at some of the code data here. And now under the code, people have posted solutions under this. And if I switch this to the most votes, the winning ones here were actually done by voting. And so this was the top vote getting one by far by this Kegel developer, Amy Young. And so we're actually using much of her code in this here. So again, we want you to just answer some questions in the write-up about this challenge and what we're going to do. And then we're going to switch over here. And then again, much of this code comes from her. Now, I have taken, we're running this outside of Kegel. You can actually do this all in Kegel if you want. We're running this outside of Kegel. So we are importing the data, and the data is quite large, so I'm limiting some. We have all the Monet style images, but not all the photos here, so that it would all fit in memory. We're filling up memory quite a bit up here with this. So we're bringing in the images here, and so we're setting up a path here. So in Kegel, this is how you'd set the path, but here in Colab, this is where we import the images here. And it'll bring in two folders, a couple folders here once we do this. So the images come in a couple of different formats once we import them. So there's JPEG style images that you can actually work with and use here. And then there's also TensorFlow has their own internal representation here, and so we actually use those a lot. These TF records, TensorFlow records. So you don't need to know about these, but the code is set up to actually use these because it speeds up training and managing the data a lot for this. So here we're reading in the data. And the TensorFlow records have a whole bunch of images in each file. So there's a couple files here that we bring in. Now the images are all 256 by 256 pixels, so they're not really large images. And then we have some methods here defined to read in and manipulate this data. And then we can actually show some of the sample images here. This is a sample photo. This is an image from Monet here. So if you remember here, what we're going to build is a generator and discriminator. So first we're going to build generators here for this. So now the generators are set up of these modules. Let's just go back up here. These sorts of modules. And so a number will make the images smaller and smaller, and then a number make them larger and larger. So we call these downsampling and upsampling layers. And those layers are a little more complicated than a single convolutional layer. So what the author does is define some methods to define each layer here. So we have this method to define a downsample layer. So this defines one of the blocks to make an image smaller here. So hopefully you can understand some of this, but you don't need to understand all of it. It creates a convolutional 2D layer. So that's what you'd think here. It also adds what's called an instance normalization layer here, and adds another leaky RLU layer, and again into this. So this is kind of a setup, and this is defined when in the paper for this. And again, the upsample is basically the opposite. It's a convolutional 2D transpose, which is the inverse of it, instant normalization here. And then we may add some dropouts here that we could specify when we create these. So each of these basically creates a convolutional, inverse convolutional layer with some additional stuff around it as needed for this. So now we're going to actually build our system. So we're going to build our generator here. So we're going to call that downsample method again and again and again. And then we're going to create a whole bunch of matching upsamples for this. as we create. So we're going to downsample, and then as we downsample, we'll increase the number of filters to a point, and then we'll max out at about 512 filters for this. There we go. And then again, when we're up sampling, again, we're going to do the same thing. We're going to start with a whole bunch of filters and then reduce the number of filters. These notes just kind of show you what size the images are. So the images start at 256 by 256. They drop down to 128 by 128, 64, 32. So the pixels get smaller and smaller here until we just convert everything into one 512 different features for this, and then we rebuild this 2x2 images, 4x4, all the way up to 256 by 256 images for this. Now you don't have to condense this all the way down to a 1x1 image. You can actually stop at 4x4, but one thing you do have to do is that your down stack and your up stack have to match. So if you were to remove some layers here, you'd have to remove a corresponding layers here also. And that will be one of your options when you make some changes to this. Okay, so that's our generator part of the network. So let's go back and look at this kind of structure. So this is it's both our encoder and this whole setup, encoder generator kind of setup. And we'll use it here and we'll use it here to take an image, do something, convert it into internal representation, and then regenerate an image from that. Now we have to also create these discriminators, which will take an image and then say output either true or false if it's real or not. So that's the second network we need to create here. Okay, so here's our generator. Okay, build the discriminator. So again, we're building the discriminator here, and again, it's pretty well a standard convolutional network. We input an image that's 256 by 256. It has 3 colors. And then we apply 64 filters, 128 filters, and 248. And again, this is using that same downsample here. So this is combining a convolutional layer with shrinking the image as we go here. Kind of our max pooling sort of idea. But instead of max pooling, we're using a newer version of max pooling up above. So that's what, okay, so we create this, and then we do some other stuff, some other normalization stuff, and set this up so that we output a model that's just predicting true or false. Is this image a real or a fake one as we go? So that's this layout here. And then now we're going to create a number of these. We're going to create a generator that generates Monet style images, a generator that generates photo style images, and then a discriminator for both. And again, the reason for that is that we're going to need to go back and forth here. We're going to need to, we're going to need to take an image. Let's say we take a normal photo. We're going to generate a Monet style photo, and then from that Monet style photo, we're going to use a different generator to regenerate a realistic photo here, and then we need to do discriminators. So we need these two generators and these two discriminators. So they're all kind of, the discriminators and the generators match, but they're going to be trained differently. So that's how we set it up differently here. So okay, so that's what's being done here with these. And now we're going to actually build our whole CycleGAN model. That whole model is coming together. So we link together all the generators and discriminators. We compile this up and link it. And again, you don't have to worry about this code. And also how we train this gets quite complicated. We have to generate a photo one way, generate a photo the other way, compare these, use the discriminators on one, use the discriminators on the other, evaluate the loss, calculate what learning has to be done, and then evaluate the loss and propagate the weight changes and all this stuff. So the learning gets quite complicated for this stuff. So I'm not going to go over too much here, but that's how this is up. And we end up needing, usually we just compare the output with the predicted output, and calculate some what we call loss, some error function that we can propagate through the weights of the network. Here we have to have 4 different kinds of loss networks, and again, I'm not going to go over how these work, but just so you know, each point in our network calculates the learning a little differently. So the loss is where we're calculating what we need to learn for this. So finally, we get down here and we can train our GAN here. So we're running this as we go. We're compiling our network here. And so here we're setting up our training, and then we call the fit function like we do with other things, and that will actually train our network with our Monet input images and our photo images, and we'll run it here. And here we're going to train it for 10 epochs. It's not very long, but again, this training of this very complicated network structure does take a long time. So each of the epochs will take a long time to run for us. So. Finally, then we can visualize our results. We can kind of see, so here's some input images, photos, and here's Monet style images here where they're trying to do it. And then you want to look at these ideas and again, kind of see how they look and what you think of these images. So, okay. Now your write-up is to kind of analyze this, do some modifications of this. So a couple things you could do is increase the training time would be an obvious one to change, because we're just training it for 10 epochs. So you could train it up to 100 epochs if you want, and see if you had time, and switch it to like a TPU for fast training. Another thing you can do is change the actual function of the generator. So in the generator, we're using these filters. We start at 64 filters and go up to 512 filters, and then 512 back to 64. Maybe you could try this maybe less, drop this down to maybe 16 filters or something like that, and then 32 filters, and see if that improves, or if the more filters help this. Another thing we can do, since we're here, we can we don't have to condense this maybe all the way down to the furthest thing, so we could delete the last couple layers, so we end up with more of a kind of a rough image at the bottom, and then we'd also want to delete or comment out. So here you could actually delete or just comment out some of these bottom lines here, and then again correspondingly comment out. So if you're going the last 2 lines here, you want to comment out the first 2 lines as we uptick these, so that our images are corresponding in size. So those are some things you can try. So your job is just pick one of them and predict, say, I think if we do this, it'll improve or not here. So it talks about some of these options here. You can also add and move dropouts when you're creating these images. You can add this dropout, apply dropout true here. So now the last thing we want you to do is look at one application of CycleGAN and make some predictions. So maybe you think CycleGANs might be really useful, could generate some really cool art. Or maybe it couldn't generate some art. So you might find an article about generating art with GANs here, or increasing resolutions. It's been used to do a number of medical image things like segmented X-rays and identify nuclei in images here. So these are some possibilities, and you're free to choose your own, do some research, do some searches, and try to look at some other applications of GANs too. Just pick one, find an article, read about it, make a simple hypothesis about that. So I hope you enjoy it for this. Good luck.